what we're going to talk about today is this really short section on 7.3. So when we were in class on Tuesday, we were talking about normality, right? And finding certain probabilities that come from a normal distribution. And what did we see happen when we tried to use normalcy, right? When we tried to use something that was normally, that was for a normal function, let's say, on things that were not normally distributed. That was our tornado example. Did it work? Did it not work? What happened?
Didn't work.
It didn't work, right? What kind of remind us of what happened there? We found a normal, the probability, I think, that tornadoes were on the ground for less than 5 miles was supposed to be in the math world, right? In a mathematical model that was supposed to be around 58% or something like that. Is that about right? Okay. So we were saying that we predict based on a normal distribution that the tornadoes in this area during that time frame would have been on the ground, if they were on the ground for 5 miles or less, would have happened about 58% of the time. But in reality, it happened closer to 80% of the time, right? And that was because that distribution was not normal. So we are incorrectly applying a model, right? Because that's all it was, is a mathematical formula in essence. We're applying a mathematical model that doesn't fit the data. Okay. So all today's lesson is about really is, okay, well, what do I do? How do I go ahead and check for the distribution of my data? If I don't already know, because I'm not told in a little sentence right there that the data comes from a normal distribution, how do I go about checking or assessing normalcy? That's what we're talking about today. Okay, and it's very short. So what we're saying here is that we are going to come up with some sort of way to quantify, right? We're going to try to come up with some sort of way to quantify that data. Now, I'm going to skip over here to something I had previous. I think this is a better explanation to show you what I'm going to talk about. So what we have here is the histogram that we're familiar with on the left, and we have something new on the right. On the right is what we call a QQ plot. And I don't really have any idea where that name comes from, but that's what it is. And what you see, does everybody see that red line that's in that right-hand graph? Everybody see that red line? All right, and what do you notice about the data, the dots? Where are the dots in respect to that red line? They're like on it, aren't they? They're pretty much lying on it. There's some that aren't. Well, what we're going to see is that if the blue lines are representing information about our data, when it lines up on that red line, that's going to automatically be, we're going to graph it, right? When we see the dots line up on that red line, it is telling us we have data that's normally distributed. Now I put up there the histogram that correlates with the data. We can see from the histogram that the data is normally distributed, right? So all a QQ plot does is it's another way for us to be able to visually see that the data is in fact normally distributed. So without pulling up a histogram, we could pull up a QQ plot and be done with it, all right? So when we are looking at the right-hand graph, that QQ plot, it supports a conclusion from the left-hand histogram. They're telling us exactly the same thing. It's just simply another way for us to be able to make that conclusion. So if we look at this one right here, that red line is our indicator, right? And notice what's happening to the blue dots there. What are they doing?
They're not on it, but they're kind of very close to the red line.
They're close to the red line, but I want you to look at the ends. Both ends. What do you see on both ends? Do what?
They're going off, like away from you.
They're curving away from it, aren't they? Right? So it's not just that we are kind of swimming around it right here in the center. If you look at the two ends that we have there, it's kind of moving away from that red line, right? So it's a different type of a function is what it's kind of showing us. You can see from the histogram on the left that this is indicating some sort of, that the data came from a uniform distribution, but this is an example of a QQ plot that does not have a normal distribution, all right, in that manner. It's not a straight line. And then the last one I would point out would be this one right here. Now that one's pretty clear, right? Those blue dots don't line up at all on that red line, which is what we're looking for. Okay, and I think that's my blue line drawn on the screen. But the left-hand graph is showing something that's a skewed right, correct? Our histogram on the left is skewed right. Okay. All right, so you kind of get the idea of what we're looking for with these QQ plots. This picture on the right is the QQ plot. All right, that's what we're going to be focusing on. So when we are talking about our distributions here, okay, it says a normal quantile plot, in other words, a QQ plot, all right, is a graph of the points where each value of the x's is from the original sample set and the y values is the corresponding z-score. So if that's the relationship to the graph that you're seeing there, okay, that's kind of just an explanation. And we use this QQ plot, right, to be able to assess the normality of what we're looking for. So how do I go ahead and do that? Well, in StatCrunch, that's exactly how we're going to do it. We're going to be using StatCrunch to be able to generate automatically these QQ plots, okay? And then we'll just kind of look at it from there. The other thing that we actually are going to be assessing, in addition to that graph that StatCrunch is going to generate, is going to have to do with this portion down here. See this inequality statement that says R is less than the critical value? So when R is less than the critical value, and you better make sure you write this down on your paper because you'll forget it. I know you will. All right. When R is less than the critical value, we end up with a distribution that's not normal. So what we're going to see is with our QQ plot, we're going to add in one more layer of identification, is all it is. Now, right, we haven't exactly talked about what R is, okay? And we may or may not get to it at the end of the semester. But let me just define for you really fast that R is what we call the correlation coefficient. It's called the correlation coefficient. And just a little backstory, do y'all remember graphing lines back in Algebra 1? You were graphing a line back in Algebra 1, all right? And you had the x-axis and you have the y-axis and it creates a line. Well, we would say that there's a relationship between whatever values were the x-axis and whatever values are the y-axis. So let's say that I have, I don't know, time and height, right? We would, if we're graphing kids' height, right? So height, the height of the child would be a relation or would have a relationship with however old the age of the child is, right? Okay, so age and height, I guess would be a better one. So there's this relationship there between the height of the child and the age of the child, right? We all agree with that? All right, so correlation coefficient R is a way for us to be able to measure the strength of that relationship, all right? And that's later on in the semester, like I said, if we get to it. But R is what we call the correlation coefficient. And so what we're going to do is, again, we have this mathematical model that's going to allow us on our QQ plot to be able to take one more step to just determine whether or not something's normally distributed. That's all we're looking at. Now, this is one of the only times in the semester where we're actually going to be reading something off a table. Now, up until now, we haven't been doing anything with any of the tables that are given, right? We've been using technology. Well, right now, we're going to actually use the table that's going to be given of critical values, and we will relate, we're going to compare the correlation coefficient R, which comes from our QQ plot, with the critical value that comes from the table. So that's how we do it, all right? So we're going to practice this example. Now, if you're in StatCrunch, all right, I loaded this data set into our group data. This is the same problem that you all have on your paper there. And it's talking about 25 years worth of data about the amount of snowfall in inches for Memphis, Tennessee. And we want to determine if we're just given the data here, or if we're looking back at the data in that case, we want to know before I move on with the data, is it a normal distribution, right? Because we can't really apply normalcy without it. That's what we're looking at here. So when I go into StatCrunch, all right, did everybody find, it's actually labeled 7.1. If you go into groups, did everybody find it? It's the 7.1 assessing normality. All right, so in the snowfall column right there, that should be the data that came from our worksheet that we're looking at. Do the first 5 of those or so look right? Just to check and make sure. All right. So how do I go about finding the QQ plot? It's a graph. So we're just going to go to graph. And then if you'll scroll down, do you see QQ plot down there? QQ plot. We have snowfall, which is the column we're using. We're going to add the correlation statistic. Let me see what this looks like when I click normal quantiles. That's what I wanted. All right, let me go back and show you what I clicked. We want to make sure that we add the correlation statistic. That's R, okay? That's R. The computer technology is going to automatically calculate it for me. And then I also check the box, the normal quantiles on the y-axis. We actually get the same conclusion whether you check that or not, but we're going to do it this time. There's the picture. Just looking at the picture, what could we say? What's our conclusion? Just looking at the QQ, just looking at the graph. It's not normally distributed, right? That's what we can conclude in this. For the most part, that's all we're going to be asking, okay? And not even which distribution, just is it normal or not? And we would say, no, it's not, right? Data's not even close to being on that line, okay? Remember that real world data doesn't always line up with, all perfect examples, but you can clearly see that this is not. Now, how would what are we going to do with that correlation coefficient? So we're going to write that down on our paper, right? Everybody write down that R is equal to 0.877. So we can see from the graph that this is not a normal distribution. Let's kind of verify that with a secondary conclusion. So that 0.877, so R was equal to 0.877, right? Okay. Now we have to compare that to the critical value, right? That's our formula from above, or that's our inequality statement. How does it compare to the critical value? The critical value comes from this table that I have on your worksheet, and it will be a table given to you in StatCrunch. So what we're looking for is I need to determine what is the sample size coming from that my data comes from. What's the sample size that we have here? Says it in the problem. 25. We have a sample of 25 years, right? Okay. So I'm going to come down here to 25 or the column, or I mean, I'm looking for 25 in the sample size column, and I can see that the corresponding critical value is 0.959, right? So I would have 0.959 is equal to the critical value. All right, now, which one's larger? Critical value. So in other words, R is less than the critical value, and our conclusion based on just the critical value, right? Just the correlation in the critical value is again the same as what we concluded from the QQ plot, that this is not a normal distribution. Just because of that one inequality statement that I highlighted in yellow above, right? When R is less than the critical value, we conclude that it is not normally distributed. So the conclusion from the QQ plot and this inequality statement should be the same conclusion. All right, that's all that's saying. Sometimes it's helpful to have this secondary idea here. If maybe the QQ plot looks a little like you're not really sure what to conclude from it, you have this backup plan right here. Okay. Now I noticed a question from the homework. It was pointed out to me yesterday. Look at the sample that the table of values right there, right? It goes through 25 and then it skips to 30, right? Now, if I look at these numbers for the critical values, what's happening to the critical values as I move from 23, 24, 25, and to 30?
They're increasing.
They're increasing, right? Okay, they're increasing. So there's a problem I noticed on your homework that asks, it has a sample size of like 40, I think. Well, you don't have a 40 in this table, but you're not really asked for the value of the critical value, but you are comparing it to the correlation coefficient. So you can assume that 40 is going to be at least 0.96 or higher. All right, make that assumption that 40 would be 0.96 or higher. All right, because we don't really have any other data based on that table. Okay. All right, are there questions on this? It's pretty simple, right? You just need to, you're just gonna, and then I think there's only 3 questions or 4 questions on your homework. It's fairly benign. All right,